This lesson is on solubility equilibria and the solubility product constant, or KSP. So we've been learning about equilibrium and our ice tables or our rice tables, and we have looked at how to handle acid-base equilibria, just a normal gas equilibria. We've looked at the common ion effect. We've looked at titrations. And now we're going to conclude this with solubility equilibria and what you would do or how you would handle a problem when you have a slightly soluble salt. So when a slightly soluble salt dissolves, it ionizes or it dissociates. Here we have silver chloride, and it is a slightly soluble salt. If you think back to our unit on solubility rules, we learned that we have certain salts, if you follow the solubility rules, that will dissociate 100% in solution. So they would not form what we would consider an equilibrium in in an aqueous system. But with a slightly soluble salt, it would form an equilibrium. Now keep in mind, we have here silver chloride is a solid. And so when you're dissolving it in water, the water is the medium that helps dissociate it or ionize it. But since this is not a very soluble salt, it's going to form an equilibrium. So you could kind of think about it as the water, if you wanted to see the water here, you could write the water in. Of course, the water is a liquid, but, in order to dissolve, you're going to have that dissolving medium, and water is your solvent here. When it dissociates, it will dissociate into the silver ion and the chloride ion. These ions will be aqueous. Ions are always aqueous. Ions cannot exist as a gas, or they cannot exist what you would say liquid or even solid. Ions in solution are always designated as aqueous, so keep that in mind. So if you were to write the equilibrium expression or the law of mass action, you would write KSP equals concentration of the silver ion times the concentration of the chloride ion, both raised to the first power, since they're in a 1-to-1 ratio. Notice we designate this as KSP, meaning solubility product. So KEQ, or just K if you will, the equilibrium constant. With acids we called it Ka, with bases we called it Kb, with pressure we called it Kp, with the water we call it Kw. Well, the capital K is your equilibrium constant, and when you see a designation, a special designation as a subscript, that is just adding more emphasis to the specific type of equilibrium system you're looking at. So just keep that in mind. These are your equilibrium constant expressions, and the K is your equilibrium constant. But we call it, in terms of the slightly soluble salt, the solubility product constant, and that's where the SP comes from, solubility product. Now, a couple of things about KSP that you want to keep in mind. KSP is constant only for solutions of slightly soluble electrolytes. So it's a constant only for solutions of slightly soluble electrolytes. KSP varies if it's a moderately or a very soluble salt. So as I was saying at the beginning, if it's a very soluble salt where you think if you apply your solubility rules, and we would say that it 100% dissociates in solution, it would not form an equilibrium, so it would not apply here. It would vary. It would not be constant. KSP increases with increasing ionic concentration. Now remember, your concentration that we use with equilibrium, the square brackets, they always mean molarity. So keep in mind that molarity, capital M, is the number of moles of your solute divided by the number of liters of the entire solution. So when we say that it increases with increasing ionic concentration, KSP, or the solubility product constant, will apply to very small concentrations, very, very small concentrations, like the ones we're going to see in our examples today. Now there's two, I guess, approaches, if you will, that you will have to a KSP calculation. The first approach is you will be calculating the KSP value from the solubility. So again, solubility, meaning the extent to which it dissolves in solution, must be expressed in moles per liter, or molarity. And again, that's what the square brackets mean. So keep in mind, those square brackets always mean molarity, not molality, not just moles, not grams per liter. It's always moles per liter. So be very, very careful about that. Units are always important. Now, in your ICE table or your RICE table, X, when you look at your shift, X represents the solubility. So keep in mind, if the problem is asking for solubility, that means you're solving for whatever the X is in your ICE table. So let's take a look at our first example. So example 1 says the solubility of lead 2 chromate, okay, solubility, meaning X in your ICE table, is 4.3 times 10 to the negative 5th grams per liter. Okay, that's important. What's the KSP for the lead 2 chromate? Now, first thing I will do is I'm going to go ahead and get my units cleaned up. So we need to make sure that we have this in moles per liter, not grams per liter. So let's just take a look at our units here. 4.3 times 10 to the negative 5 grams per liter is what they gave you. I'm just going to use a little dimensional analysis here. There's a couple of ways you could approach this. You could, maybe do it as in a two-step type way, but I'm going to just go ahead. I need moles per liter, so that means I need moles on the top and I need liters to stay on bottom. Okay, so we want to think about what do we know that we can use that will get grams to cancel out on bottom. What's your units? And we need moles on top. Well, if you look at these units, you see that that is the unit. Those are the units for molar mass. So it's always grams per mole, right? So if we calculate the molar mass of the PbCrO4, so the lead is 207.20. That's from our periodic table. The chromium from the periodic table is 52.00. And then, of course, we have 4 oxygens, so 4 times 16 is 64.00. So if you add these together for the molar mass, that's going to give me 323.20 grams per mole. Okay, so again, we're just doing some basic stoichiometry here. We're going to plug in that molar mass, 323.20. This is going to let your grams divide out, and it leaves you moles per liter. So we're about ready to be rocking and rolling with our units. Always watch your units, y'all. So as I plug that in, I get 1.3 times 10 to the negative 7th. And now we have moles per liter, or molarity. So now we have that unit in the proper unit. So now we can continue with our ICE table. So remember, this is the solubility, which is our X in our table. Now, I want you to make sure, because I noticed that some of you are having issues with like some of your final answers when you're solving. And I think those of you, it looks like those of you that are having trouble, it's because you're not writing your equation. So I'm going to require that I'm looking for your reaction. So I need you to write that out from here on out. PbCrO4, Keep in mind these are slightly soluble salts. They are solids initially before you dissolve them in water. We're going to always put our equilibrium sign here. As you dissolve that in water, you want to think about how will this dissociate? Well, this is lead 2, so it's going to form 1 because there's 1 lead in the formula. 1 lead 2 ion, and that's going to be aqueous. And it's going to form the dichromate ion, the chromate ion, not dichromate, CrO4 minus 2, and that's going to be aqueous. Now, you don't have to write the AQs here, but I'm writing it for this first example because you must understand that these ions have to be aqueous in solution. All right, so initially, if you do think in terms of your ice table, I'll do rice because we do have the reaction. Initially, you're told, well, first of all, this is a solid, so solids don't even matter, so you don't have to put anything here, okay? But initially, it would not have dissociated before you put it in the water, so you're going to put 0, 0. But the change will be your solubility or your X. And if you think in terms of stoichiometry, it's going to always shift to the side where there's the hole, if you will. It's going to shift to the products here. So plus X plus X. And that means at equilibrium, we know that X is our solubility, so 1-to-1 ratio. So X is going to be 0 plus X. X is going to be the concentration of the lead 2 ion. X is going to be the concentration of the chromate ion. So let's write our KSP. So KSP, and we're going to write it completely out. Don't take any shortcuts here because this is where you end up getting into a lot of trouble because you overlook things. So it's going to be PB2 plus, and that's to the first power, and that's going to be equal to CrO4 minus 2, and that's to the first power. Now, if you substitute in from your rice table, if you substitute in these values in terms of X, that means KSP is equal to X times X, which is X squared. So I'm going to do a little bit of the math here. We just said that the X is equal to your 1.3 times 10 to the negative 7. So KSP is equal, like substituting your X value into your law of mass action. So 1.3 times 10 to the negative 7 molar, and that's quantity squared. And now we have our KSP. When you square that, you get 1.7 times 10 to the negative 14. And the unit there is molarity squared. And that's your KSP value. That is your constant. Let's move on to our next example. All right, example 2. This is calculate the KSP again of silver chromate whose solubility is 1.3 times 10 to the negative 4. So notice this is in molarity already, so there's nothing to convert. It's already in molarity. This is your solubility, which means when we do our rice table, this is going to be our value for X. So let's write our rice table out. So that means we need to start with our reaction. Ag2, CrO4, solid, in equilibrium. And so when this dissociates, notice there's 2 silver ions, so 2 Ag pluses. These are ionic equations. Silver has a +1 charge. That's aqueous. I'm not going to write it on this one because remember, all ions have to be aqueous in solution. CrO4 2 minus, there's one of those. All right, and we're going to do our remember, solids are ignored, solids and liquids. This will be 0, 0. So this is going to be in this rice table plus 2 times X. This is where you got to be careful, y'all. Plus X. So at equilibrium, 0 plus 2X, that means the value for the silver ion is going to be equivalent to whatever 2X is, and the value for the chromate ion, I keep trying to call that dichromate, y'all, I'm sorry. For the chromate ion is going to be equal to X. So let's set up our KSP, or our law of mass action. KSP is going to be equal to concentration of the silver ion, and that's going to be quantity squared. This is where you want to do not take shortcuts because it's very easy to mess up on these. These are pretty easy to do, but it's also easy to mess up if you take shortcuts. This is going to be CrO4 minus to the first. Now substitute in these values from our rice table. That means KSP is going to be equal to 2x, that's quantity squared, and that's going to be x to the first. So KSP, this gives you 4x quantity squared times x, and so KSP is equal to 4x cubed. Now we just said that our x value is equal to the solubility, and that was given. So KSP is equal to 4. Now substituting your x value, 1.3 times 10 to the negative 4 molar, and that's quantity cubed. Plugging that into your calculator, cube that, and then multiply by 4, you'll get 8.8 times 10 to the negative 12. Unit will be molarity cubed. This is your solubility product constant for this particular silver chromate, and notice it is a dilute solution. It's a low concentration. Moving right along. Now, what if you're asked to calculate the solubility? So find the x, but they give you the KSP. So let's look at some of those examples. Remember, the solubility is your x value, and it's always in molar solubility or molarity. So the solubility or x of a sparingly soluble or slightly soluble salt can be calculated from the KSP. So for example, one of this particular type is says the solubility product for silver chloride. So silver chloride is AgCl is 1.8 times 10 to the negative 10. So that's the solubility product. So that means they're telling you here the KSP. Again, watch your wording. Make sure you're familiar with the vocabulary. You're going to do your reaction, Ag plus, and then Cl minus. These are both aqueous. Again, make sure you're writing your entire reaction out. Do your ice table. Remember, I'm requiring this for full credit. All right. So it says calculate the molar solubility. So we are just asked to find x here. We're looking for whatever the value for x is. So again, 0, 0. This will be plus x. This will be plus x. So x, set up your law of mass action. That would become KSP equals concentration of the silver ion times concentration of the chloride ion. KSP is equal to x times x, or x squared. Remember, we're looking for x here. The KSP is what they gave us. So we're going to plug in 1.8 times 10 to the negative 10 for KSP, and that's equal to x squared. Of course, take the square root of both sides to isolate your x. When you square root that, you get x is equal to 1.3 times 10 to the negative 5th molar. That is your solubility. So as you see here, these are pretty simple as far as the math goes, but you got to be careful with your reactions and how you define x and the wording. Let's look at another example. 16th century physicians used calomel as a medication. Their patients did not usually die from mercury poison because the calomel is a sparingly soluble compound. Calculate the molar solubility, so it wants us to find x of calomel, and it gives you the KSP. So again, they want you to find x, they give you the KSP. So the formula for the calomel, Hg2Cl2. So y'all all have heard of amalgams. They've used them in dentistry. They do contain some mercury, but this is explaining why most people did not die from mercury poisoning. So, all right, mercury, if you pull this apart, your mercury 1 ion is Hg2 plus 2, and then you have the chloride ion. Now there's 2 chlorides in the formula. Okay, so this gives you a 1:2 ratio. So there's your dissociation of the reaction. You can do your ice table. Solids are ignored in your equilibrium expressions. This is 0, 0 as usual. Plus x, this would be a plus a 2x. So the mercury 1 ion will be equal to the concentration, will be equal to whatever x is, and then the chloride will be equal to whatever 2 times x is. Let's write out our law of mass action. Hg2 plus 2. So mercury 1 ion is actually a polyatomic ion. It's not one we see a whole lot, but here we are seeing it. So it's good that y'all are able to see that. Now we're going to substitute in KSP. We're going to substitute x here, 2x here, and that'll be quantity squared. So KSP is going to be equal to 4x cubed again. All right, let's substitute in here. Remember, they gave us the KSP. I'm going to go ahead and continue this up here. So 1.1 times 10 to the negative 18 equals 4x cubed. Now, you might want to pause the video and finish this one out on your own. I'm going to go ahead and keep working it out, but just make sure you're working through these and y'all are able to get the same answers I get. Make sure that you always are checking to make sure you get the same answers that I get. Now, we're going to divide both sides by 4, right? And then we're going to take the cubed root, okay? And that's going to allow us to solve. So when I divide by 4, I'll go ahead and break that down. I got 2.8 times 10 to the negative 19 equal to x cubed, and then take the cubed root or raise it to the 1/3 power. And that's going to isolate your x. And remember, x is always, if you're looking for solubility, it's in molarity. So 6.5 times 10 to the negative 7. All right. Hopefully you got that right. Make sure any of these you're having trouble with, you shoot me a message. All right, now let's look at one last example. Solving solubility, what if you have a common ion? So for this example, it says for the salt silver iodide at 25 degrees Celsius, the KSP is 1.5 times 10 to the negative 16. What is its solubility, though, if it's in a 0.05 molar sodium iodide solution? Now remember, sodium iodide is a very soluble salt. It will 100% dissociate. So this is where we're looking at Le Chatelier's principle and the common ion effect with a solubility problem. Notice these are two different salts, but they both have a common ion, the iodide ion. All right, so let's take a look at this. So you would first go to your slightly soluble salt. That's the one you want to write your reaction with, and this would be an equilibrium. You're going to dissociate it. Now you're going to write your ice table out, and we're going to remember that the solids are ignored, so we're not going to put anything here, here, or here. And here, normally we go 0, 0, but since we have sodium iodide, common ion, it dissociates 100%. We have a concentration here. So notice, okay, we have an initial amount. So we do our shift, the zeros here, so plus x, since it's 1 to 1. And that means at equilibrium, silver ion would be equal to x, and the iodide will be equal to 0.05 minus x. Now remember, we can ignore x if you have an initial amount present. So this is going to greatly simplify our problem. So just keep that in mind. We can't ignore the x. So that's why when you write out your law of mass action, notice here initially I plugged it in as x and 0.05 plus x, but we can ignore the x here. Get my pen tools back out. So we're able to ignore this x here. So utilizing the 5% rule, simplifying our problem, you have 1.5 times 10 to the negative 16 is approximately equal to x times 0.05. Divide both sides by 0.05. Let me write that in. 1.5 times 10 to the negative 16. We're going to divide by 0.05. Divide by 0.05. I didn't show that here when I typed it out. That gets rid of it over here. Isolates your x. So x is 3.0 times 10 to the negative 15 molar. So notice what happens with that common ion. By the addition of that common ion, the solubility is 3.0 times 10 to the negative 15. So it shifted it where it's not quite as soluble, okay, because of the presence of the common ion. All right, so you handle those very similarly. I hope you see, as you would with an acid or a base with the buffer problems. All right, that's it for this video lesson.